to record it. So we are going to talk about distribution, and this would be distribution with the protein binding, penetration into the fat depots, how we would have distribution for the blood-brain barrier and into the placenta barrier as well. Okay, so we have already seen this one, and we know that anything which is bound will not move. Whereas anything which is free can move freely from one compartment into another compartment. Therefore, only the free drugs would be moving. Now, we know that the free drug will reach the extravascular space, and this process of distribution is reversible. And the physiochemical properties of the drug which affect the distribution alter pharmacological effect, toxicokinetics, and the drug interaction as well. So how are these things? In case of the body fluids, you know that body has a total content of 40 to 42 liters, and the vascular is about 5 to 6 in these cases. Also, the blood flow is considered to be rapid and slow equilibrium. In case of the rapid equilibrium, lung, hearts, kidney, they all have a very fast equilibrium, whereas the slow equilibriums are the ones which have the muscle, the fat, the bones. These are the ones which have the slower equilibrium. We will talk about protein binding first. So when we talk about protein binding, just look at the word. What does it mean? Binding of the drug to the protein. So that's protein binding. What are the different proteins that we have? Albumin, I'm sure all of you have heard about it. We have globulin, glycoproteins, and depending upon the kind of protein, the drugs that bind to them will also vary. Example, albumin, which has got a 69,000 Dalton, will bind to neutral and acetic drugs. Examples of those drugs are ibuprofen and phenytoin. Likewise, lipoprotein will bind to lipophilic drugs, imipramine and cyclosporin A. Also, when we talk about plasma protein binding, we talk about a concept called as the free fraction. What is free fraction? Look at the first figure. In the first figure, I had put that the drug is given as the crescent and the protein would be as the circle. Now, when we have 5 drugs and 5 protein, what is going to happen? The number of drugs is equal to the number of proteins. So there will be it will be bound, which means the drug will be completely bound to the protein. So if it is fully bound, is there any possibility of a free drug? There is no free drug. Therefore, what will happen? The efficacy of the drug will not be there because it is bound. Only when a drug is in free form, it will be able to act. Now, you look at the second figure. What do we have? It's the same amount of the protein, but the amount of drug that we have given is higher. So what is going to happen? 5 drugs would be bound to the protein, but the rest of the 5 would be free. Okay, so because there are 5 free drugs, then it can be able to act. So that is what is called as the free fraction. The fraction of the drug which is free and not bound to the plasma is called as the free fraction. Now, what is free fraction? Fu is equal to Cu by Cp. What is this? Now, Fu is the free drug fraction or the unbound drug, whereas Cu is the unbound concentration, meaning it is not bound to the protein. And Cp is the total plasma concentration. So if I give you this formula, Cu is equal to, Fu is equal to Cu by Cp, then you will be able to calculate. If Cu is 25 and Cp is 100, you will know immediately 25 by 100, that would give you 0.25. And likewise, the same other would be considered for the other one. So if it's 15 by 50, it would be 0.3 and so on and so forth. These would be the normal questions which I would be giving you activity, but since we are doing it online, we're just going through with it. Next, we are going to talk about the fat depots. What do we have in fat depots? The fat depots, the tissue distribution and penetration is significantly less steady. Outside the plasma, drugs bind to the non-aqueous depot. Remember all those words that I was talking about? Non-aqueous means aqueous and non-aqueous. So you know that it is lipophilic. So these would be the tissue proteins, DNA, RNA, and fats and lipids. In case of the kinetic aspects, it is reversible. Remember, we have this distribution is reversible, and this is also reversible. What about the bonds? It would be the van der Waals bonds or the hydrogen bonds. Larger variety of drug protein complexes are available. What are the PK consequences? PK is the pharmacokinetic consequences. They act as a reservoir of drug, which means that when the free drug has been removed from the plasma, the drug which is bound to the protein comes out. Remember, it is reversible. Therefore, the bound drug will be released when the free drug is completely over, therefore acting as a reservoir for the drug. Okay, so that is a reservoir for the drug. And it can also prolong the pharmacological effect and slow the return from the depot as well. So that is another thing that we can talk about over here. Blood-brain barrier. We all know where is the blood-brain barrier, right? So that is in the brain. And this, what does it do? It helps in the sending water, oxygen, and glucose. So this is the blood-brain barrier in a schematic that we have. And distribution across the blood-brain barrier is very significant, and we need to know how it works. For example, when a patient has meningitis, what is meningitis? Split the word. Meninges is the covering of the brain, and itis would be the infection and inflammation rather. So we'll be giving the antibiotics to control the infection. So since it is there in the brain, the drug has to cross the blood-brain barrier and enter the brain. So that is very important in that case. Likewise, dopamine in case of Parkinson. We all know that Parkinson is a disorder in the brain. Likewise, anticonvulsant therapy, which is for the phenytoin and lipid-soluble drugs like the propranolol. All these cases, the penetration process, the drugs are lipid-soluble or very small molecules. They cannot cross the blood-brain barrier if the molecule is too huge or if it is water-soluble, because the brain is a lipid membrane. Therefore, we need to have this lipid solubility and the small molecule. That is a very important thing in case of the blood-brain barrier distribution. Then we have the placental barrier. What is this placental barrier? We all know that placenta is the one where the fetus are quite nicely tucked inside the mother's womb. So in this case of absorption, again, the same things, high lipid solubility. And look at these drugs, sulfonamides, barbiturates, anticonvulsants, narcotics, and all these things are highly lipid soluble. So we need to have these ones which are high lipid soluble, only can cross the placental barrier, again, because we know that the membrane is a lipid membrane. Okay. And we also have very limited research on the humans in case of this, and because we know that there are some serious cause fetal abnormalities. Therefore, there is very limited research on the humans in this case. And can we use these drugs can be used to positively treat the fetus as well. Now look at this figure. Absorption mechanism. This side is the mother and the other side is the fetus. If there is a polar drug, then the drug cannot enter the fetus. However, if the drug is non-polar, it can enter. And we know that distribution is reversible, therefore it is a reversible process. Also, this is a polar metabolite. If it is a polar metabolite, it cannot enter. If it is a non-polar metabolite, it can come back and forth into the membrane and across the placental barrier as well. Now we remember that drug, absorption, systemic circulation, distribution, elimination, and all these things we know about it. And we saw about free fraction. Now we need to talk about the volume of distribution. We need to recognize what is the distribution of the drugs and how do we describe it, what is bioavailability and what is a volume of distribution. So we will talk about a little bit about the zero and first order kinetics. Volume of distribution. In case of the volume of distribution, look at the word. How much is the distribution in terms of volume? That is volume of distribution. What is the distribution of the drug in terms of the volume. That is the volume of distribution. Now this parameter, this is a very important formula for you to remember, just like the free fraction. V is equal to D by C. What is D? Dose. C is the concentration. In case of the dose, it's a dose administered. For example, Panadol, if we are giving 500 milligram, so that is the dose which is administered. So 500 milligram is the dose which is administered. Plasma concentration is the concentration that is available in the plasma. Will that be 500 milligram? Never, because it's a too high an amount. And then there are so many steps and processes in between that the amount, the concentration of the drug which is entered the plasma would be very, very less, would be in nanogram or in picogram. Then we talk about the apparent volume of distribution. The body behaves like a bucket. Look at this figure over here. So we say that let's assume that the body has about 1 liter. And in this case, in this 1 liter of the blood, what is the dose that we give? 100 milligram. So if this dose is 100 milligram, what is the concentration here? It is 100 milligram per liter. Why? The dose is 100 milligram and the volume of the bucket is 1 liter. Therefore, 100 milligram per liter, that is the concentration. So we know the dose and we know the concentration. So what would be the V? V would be the 100 milligram, which is the dose, and 100 milligram per liter, which is the concentration. Remember, the formula is V is equal to D by C. Now let's look at this. This is the scenario 1 that we already spoke about. Let's talk about scenario 2. What is happening here? Do you see this blue marker over here? It means that the tissue uptakes 99 milligram of the drug. When 99 milligram of the drug has been taken, what would happen? How much is left over here? 100 milligram of the dose minus 199. So that will give you 1 milligram. I repeat, the dose is 100 milligram, but the tissue has taken up 99 milligram. So what is the concentration? 100 minus 99. That will give you 1 milligram per liter. Now let's use the formula and substitute these values. So you would get 100 milligram by 1, that would be 100 liters. So this is how we calculate the volume of distribution. Look at these scenarios. Drug A, drug B, and drug C. What do we have here? We have the protein and we have the drug. In case of the first one, the volume of distribution is very uniform. How do we know? Look at this one. In the blood and in the tissue, the drug is the yellow color squares which are there. They are very equal in amount, right? So we have equal distribution. But let's look at this one, drug B. What is happening here? The amount of drug which is present in the blood is very high. Therefore, the volume of distribution in the tissue is very less, okay? Whereas the volume of distribution in case of drug C is very high. So the tissue distribution is very high in case of the drug C. That's why we say that it is a large VD and therefore we have the numbers also going in that effect. So you understand that volume of distribution is the distribution of the drug in terms of volume, mostly in the tissue. So that is how we calculate the volume of distribution. And you, from figuratively, you also know how to see and schematically understand how this is happening in case of different drugs which have no protein binding. B has got a high plasma protein binding and C has a high tissue protein binding. Volume of distribution, as we have said, if it's only from 1 to 7, it's confined to the plasma. However, if it is more than 7 to 42 liters, then it's get distributed all over the tissues. Okay, and if it is more than 10,000 liters, it is most of the drug is in the tissue fully. The larger the volume of distribution, the more likely the drug is found to be in the tissue. The smaller the volume of distribution, it will be bound only in the blood or the circulatory system. Let's talk about plasma level time curve. From the word, what do we understand? Amount of plasma which is present, the amount of the drug which is present in the plasma versus the time is the plasma level time curve. Now let's look at the intravenous graph. This intravenous graph, you can see that it was given at 0.6 milligram per kg. This is given and it has spiked from 0 to 500 and almost 550 milligrams in here, and then it is dropping down slowly. Whereas if we look at the oral, where it is given at 2 milligram per kg, it is slowly picking up and goes only up to 300 milligram, even though the amount of the drug given is 2 milligram. So this is the plasma level time curve, and this gives us a very good understanding of how the drugs are entering into the plasma, which is the absorption. And we can establish a mathematical model by means of the first order kinetics and by understanding what is the compartment of the model. Remember, we had fast equilibrium compartment, which is the heart, lungs, and we also had the slow equilibrium compartment, which would be the muscles. Now, we all know this graph where we have the PK/PD link, pharmacokinetic, pharmacodynamic link. The concentration is on the y-axis and the time is on the x-axis. We know that after a certain degree, the drug concentration becomes toxic, and below the certain concentration, it would be the efficacy level that would be happening. In case of the first order kinetics, it depends only on one variable, which is mostly the concentration of the drug. So if we say that the percentage per time is 20% per hour, then it's a very constant one. So in case of the 20%, look at this one. The first order I had given you in the table below, T is equal to 0 if it's 100. For the first order, if it is 10%, I'd given as 10%. So 10% of 100 would be 10, correct? So 100 minus 10 would be 90. And then from the 90, the 10% of 90 is 9. Therefore, 90 minus 9 would be 81. So on and so forth. If you look at the 1000, it would be the same as well. 10% of 1000 would be 100. So 1000 minus 100 would give you 900. Likewise, the 10% of 900 is 90. So 900 minus 90 would give you the 810. So this is what we have in case of the first order. Let's look at the zero order kinetics. In case of the zero order kinetics, it is not dependent upon anything. It is independent. So if we say that it's 20 milligram per hour, then you look at this one, 100 minus 20, 80. 80 minus 20 is 60. Likewise, even if it is 1000, because it is not dependent upon the concentration, what would be happening is that 980. And then 960 because it's only minus 20. So that is the difference between the first order kinetics and the second order kinetics. IV bolus administration. What is the difference between IV bolus and IV infusion? IV bolus is the one where we give directly 20 milligrams of the drug or the 25 milligrams in one shot within a short period of time. Whereas when we talk about the infusion, it is given over a longer period of time. Let's say for hours, like 60 minutes, 120 minutes, those kind of times we are talking about. When we talk about the IV bolus, the volume of distribution, the CP is the concentration of the drug in the plasma and T is the time in hours. This would be the concentration at the 0 hour because it's bolus. Remember, one shot you're giving it. Therefore, it does not start at 0, but it just goes straight with a higher amount of the drug being given there. Okay. So that is what we have. And then it slowly goes down. And this is given as a log value by here. And volume of distribution, we know that V is equal to D by C. And you all know that half-life. What is half-life? The time that is needed to reduce the drug concentration by half at any time. So that is the half-life. I'm sure you have studied all the half-life in your A levels in your previous semesters as well. Now, half-life is the amount, the time that is needed to reduce the drug concentration by half at any time. So the formula is T half is equal to 0.693 by KEL, where EL is the elimination rate constant. EL is elimination rate constant. So if it is 20, then what is the time taken for it to go to 10? So that is what we would be calculating in here, and that would be considered as the half-life in this case. Why is half-life important for us? Because elimination half-life determines how long does it take for the body to eliminate it out of the body, which means that the efficacy is totally taken out. That is why it's very important. Let's look at the graph over here. Now, if we look at it, I put the number of T half in the x-axis and the percentage of the drug which is remaining in the y-axis. It starts at 100 and then it drops down quickly. And then once you look at this from the 4 to 6 to 8, it's just gradually coming down. The same has been depicted in the table. So percentage in the body is 100 and percentage eliminated is 0. Whereas in case of the first T half, it's 50-50. Now you look at this one for the second T half, 50 by 2 would be 25. So what is the amount left in the body? 25. The longer the half-life, the longer it takes to eliminate from the body. So if we have a drug which has a longer half-life, then it takes a longer time for it to eliminate, which means that the effect of the drug on the body is longer. Okay, and it takes 5 T halves to eliminate 97% of the drug. Is this a very important number? Absolutely. This is a very important number for you to remember. It takes 5 T halves to eliminate 97% of the drug. Extravascular administration. Split the word. What is extravascular? Outside the circulatory system. Examples of extravascular administration would be oral, all those things, local. Okay. Now let's look at this. Tmax is earlier when Ka is earlier. What is Tmax? The maximum amount of the time. Look at the brackets over here in the bottom. What is Ka? A is absorption rate constant. When the absorption is very quick, then what is happening? The amount of the time taken to reach the maximum amount of the drug is very quick. If there is another drug whose absorption rate is very slow, then what would happen? The time taken to reach the same amount of the drug would be very slow. So that is what it means. If Ka is higher, Tmax is earlier. If Ka is slower, Tmax is much later. So that is what we have. Ka is the rate absorption constant. Elimination rate constant, we already saw that half-life is T half, it is 0.693 by KEL. But remember that the absorption rate constant does not have any influence over the T half. Whatever is the amount of the drug which is in the blood will be taken into consideration. Therefore, the Ka does not have any effect on the half-life of the drug. We have already spoken about elimination rate constant, half-life, volume of distribution, Tmax, Cmax, elimination rate constant, and half-life as well. We are going to talk about a very important concept now, which is clearance. Okay, clearance. This is the eliminating organ. What are the usual eliminating organs? We have quite a lot of them. We have the kidneys, which removes the urine. Along with the urine, it removes a lot of the drugs. Also, feces would be eliminating it as well. Then there is lungs, which will eliminate some of the things. And then you also have the liver, which helps in the metabolism and in the clearance of the drugs. So these are some of the eliminating organs. Now, if we look at the picture on top, C in is equal to C out, meaning the concentration of the drug which enters inside the organ and the concentration of the drug which goes out of the organ. So that is C in and C out. Elimination ratio is C in minus C out divided by C in. Let's say that we have 100 milligram of the drug which goes inside, but only 25 milligram is coming out of the organ. So what does it mean? 100 minus 25, 75 milligrams has been eliminated. So that is what it means. Okay. If there is complete removal, if there is 100 gram going in, 100 milligrams going in, and 100 milligram has already been taken out, that means eliminated, the C out would be 0. And therefore, we will calculate it accordingly as well. So ER has no units because it is a ratio. Clearance, is the clearance only calculated based on only one organ? No, it is calculated on many different organs where the drug is being metabolized. So hepatic plus renal plus saliva. So all these things, very important to establish the dosage schedules. As we said, clearance is the most important parameter in pharmacokinetics. Now we know that this is the drug absorption, systemic circulation, distribution. And now we will be talking about elimination.